Hello again. This is Math 2233 coming to you from the College of DuPage. The title of this lecture is Derivatives and Integrals of Vector-Valued Functions. And I encourage you, as always, to be an active learner when watching this video. In the future, we're going to use vector functions to describe motion and even acceleration of objects through space. And so here we prepare that by developing a review of the calculus of vector functions. So let's start by defining the derivative. So the derivative of vector r with respect to t is r prime of t. Notice this is bold, so it is a vector. Is the limit as h goes to 0 of r, the vector valued function at t plus h, minus r of t, all divided by h. And of course, if you picked t to be a specific value, you get a number. So for this reason, the vector r prime of t, it is still a vector, is called the tangent vector to the curve defined by r at the point P, provided that r prime of t exists and r prime of t does not equal to 0. And so you can see that it's the limit of these secants for this space curve C as t goes to 0. And so in the limit, it's going to be the tangent r prime of t. And the direction of r prime of t is going to be in the direction that it goes when t is increasing. So the tangent line to C at P is defined to be the line through P parallel to the tangent vector r prime of t. Realize that r prime of t is a direction and magnitude, but you can put the endpoint anywhere. We will also have occasion to consider the unit tangent vector, which is defined as capital T of t, again a function of time. So capital T is r prime of t divided by the magnitude of r of t. And of course, this can only be done when r prime of t does not equal to 0. But this tells us the direction of the, how is the tangent of the curve changing with respect to time. Now, secant vectors, and in fact the derivative vectors, the limit of the secant vectors, can be drawn for any space curve. And we use the secant vector to move closer and closer to each other. It becomes closer and closer to the tangent vector. So a space curve can model the path of a softball as it's thrown by a pitcher. Secant vectors on the curve show the average velocity between points. As those points move closer together, the secant vector approaches the tangent vector, which gives the instantaneous velocity. In a similar way, physicists study the path of particles through magnetic fields by examining space curves. A secant vector gives the particle's average velocity, and as the intervals used for the secant vector become smaller and smaller, the secant vector approaches the tangent vector. The final example here, engineers design roller coasters to meet certain specifications. The secant vector for the roller coaster's position gives an average velocity over an interval. As that interval becomes smaller, the average velocity approaches the instantaneous velocity, which is shown as the tangent vector. And so here's a theorem, and it's not a surprising theorem, but it is an important theorem for your calculations. So if r of t is equal to pointy bracket f of t, g of t, h of t into pointy bracket, or in the ijk direction, where f, g, and h are all differentiable functions, then r prime of t is equal to, you just take the derivative of each component, and it can be represented this way. And the proof of that follows by using the definition. So this is a limit as delta t goes to 0 of 1 over delta t. And this is r at t plus delta t minus r of t. And so we do the vector algebra. We get this. And we move the limit inside the vector, and we take the vector limit, and we get this. So you see, to find the derivative, you just take the derivative of the components. So let's try this out. Let's do two things. Here there are two things for you to do. Find the derivative of r of t, which is equal to this vector valued function. And then after you do that, you want to find the unit tangent vector at the point where t is equal to 0. You know what to do. Let's see how you did. So when you take the derivative of this is going to be 3t squared. This you have to use the product rule and simplify, but when you do that, you should get something equivalent to 1 minus t e to the minus t. And when you take the derivative of the sign, you use the chain rule, and you get 2 cosine 2t. So that is the derivative, and make sure you understand how to get this. But now we're going to be substituting 0 in here, and so when we substitute r of 0 into this expression, we get I, and r prime at 0, we put 0 in here for t, that you're going to get j plus 2 k, and so the unit tangent vector at that point is going to be r prime at 0 divided by r prime at 0 magnitude, so you get this, and you get this as the unit vector. Make sure you understand these examples. These are the kinds of problems I sometimes will ask. Now, another problem for you to consider. For the curve r of t equal the square root of ti plus 2 minus tj. Now, it looks like this could be in 3 dimensions or 2 dimensions. I'm guessing it is in 2 dimensions, but it could also be in 3 dimensions, but certainly this is in the xy plane. Find r prime of t and sketch the position vector r of 1 and the tangent vector r prime of 1. You know what to do. Let's see how you did. Okay, so when we take the derivative of that, we're going to get r prime of t is equal to 1 over 2 square root of ti minus ij. And then when we put 1 in, we will get this expression. So the curve is a plane curve. Now, and in fact, if you were to graph this, you would get the blue curve. The tangent is the vector here, and you can see that this is the direction of the vector as t gets bigger is going down. Actually, it's a constant. It's always going down. And notice the tangent vector points in the direction of increasing t. And so that's what we have. Here's another problem for you. Now this is should be starting to become a bit of a well-known curve. It's not exactly a helix because you have 2 cosine t, but it's kind of a lopsided helix. And I guess it's still called a helix even though it's not a circle. It's more of an ellipse in the plane z equal to 0. But here are the parametric equations, and so you want to find the parametric equations for the tangent line at this point, 0, 1, pi over 2. You know what to do. Let's see how you did. Okay, so here is the derivative. This is the vector equation. And so we take the derivative, we get minus 2 sine t, cosine of t, and we get 1. And if we take the value to be 0, 1, pi over 2, and so that's going to be, t is pi over 2. So the vector is going to be r prime of pi over 2 is minus 2, 0, 1. Now the tangent line through this point then, parallel to this vector, is given by this parametric equation. And so you see that x is equal to minus 2t because we had the 0 there. Y is simply 1. And z is going to be 1 times t, and then we get pi over 2. And if we looked at that, we would see that that is indeed a helix. It is got an ellipse on the bottom, but here is the tangent line that we're looking for. Now, just as for real valued functions, The second derivative of a vector function r is the derivative of r prime. So you take the derivative yet again, and in this case, the second derivative of the function would end up being this, and that's the second derivative of the function that we were just studying. And you might want to check that you get that as well. So the second derivative would be pointy bracket minus 2 cosine t, comma, minus sine t, comma, 0. And there you see the example finished. Now note that you see how r prime and r double prime can be interpreted as the velocity and acceleration of the vector of particles moving through space. This is not surprising, and we'll deal with this in a later section more explicitly. Now, there are rules for taking derivatives, and none of these are very surprising, but we should review them. So suppose u and v are differentiable vector functions. C is a scalar, and f is a real valued function. Now you see this f is not a vector, it is a real valued function, a scalar valued function. And so it is a function of t. So then, and we're assuming all these derivatives exist, the derivative of the sum of the vectors is the sum of the vector derivatives. You can factor a constant through the derivative sign, and the product rule works in this case, an instance where you have a scalar function times a vector function. It works the same way. It's the same old product rule. And here, if you have a vector function dotted with a vector function, and again, that's the form of multiplication that you have here. Here it's normal multiplication. Down here it is the dot product. But you see it is going to be u prime v, the dot, u prime dot v, plus u dot v prime. Here, if you're taking the cross product is going to be having this product rule, u prime of t cross v of t, u of t cross v prime of t, and if you have the chain rule, which is the composition functions, again, you take the derivative of the outer function, which is going to be a vector derivative, times the derivative of the inner function, which in this case is a scalar function. So you have chain rules. So these are what we have. The only one of these that we're going to bother looking at the proof is this number 4. So you let u be this thing with the f's sub i's, pointy bracket, f1, f2, f3, and v is going to be pointy bracket, v1, v2, v3. Then the dot product is going to be the product of these individual functions, which can be written that way. So when you take the derivative with respect to t, you're taking the derivative of each one of those, but then you can reorganize it and get the right-hand side from equation 4. And again, that's a proof of 4. You should be able to prove all of these, but more importantly even than that, you should be able to use all of these. Now, this is a result. I'm asking you to work on this as an exercise, but it is an important result. Show that if the magnitude of r of t is a constant, then r prime of t is orthogonal to r of t for all t. We're going to use this result repeatedly in what follows. So it is an important result. You know what to do. Let's see how you did. Okay, so we're going to use the fact that if r of t is a constant, then if we square the magnitude of r of t is a constant, if we square it, we get c squared, so we get r dotted with r. So now we can just take the derivative of both sides. Now the derivative of this side is just 0 because the derivative of constant is always 0, but here I have to take the product rule. So I get r prime of t times r of t plus r of t times r prime of t, and that is 2 r prime of t dot r of t. Now, so you have 2 times this 2 times this expression, and the dot product is going to be a scalar. So 2 times this scalar is going to be 0. That means that r prime of t dotted with r of t is equal to 0. And that says that r prime of t is orthogonal to r of t. Now, geometrically, and we can look at the picture, this says that if a curve lies on a sphere with center at the origin, or actually center anywhere, then the tangent vector is always perpendicular to the position vector, and that's something that you learned in geometry even before this, but now you have a vector definition of it. Let's talk about integrals a bit. The definite integral of a continuous function r of t, and this is a continuous vector function r of t, can be defined in the same way as a real valued function, except that the integral ends up being a vector. But then we can express the integral of r in terms of integrals of the component functions as follows. So this is the notation. So the integral, this is going from a to b, is, and you can see it's a limit of finite Riemann sums. It's going to be this. And so your end result is that the integral from a to b of r of t, f of t, you have the integrals for each of the components. Now notice that when we get arbitrary constants, that is going to end up being a constant vector, not just a constant number. And so we can then evaluate these integrals of a vector function by integrating each component function. And so the fundamental theorem of calculus states that if you're integrating from a to b, lowercase r of t dt, that is capital R of t, that is a vector evaluated at b minus the evaluated a, and again we're using the same antiderivative, so you might as well take the constant when you're computing a definite integral to be the zero vector. And capital R is the antiderivative of lowercase r, because if you take the derivative you get this. And so this notation is for indefinite integrals, and here you would have an arbitrary vector, constant but a specific vector as your constants of integration. So here's a problem for you to do. So if r of t is equal to 2 cosine ti plus sine tj plus 2t times k, then find the indefinite integral of it and evaluate this as a definite integral from 0 to pi over 2. You know what to do. Let's see how you did. So this is what we get, and this is the constant of integration that we have. Now, if we, and this is a vector, so it's a vector constant of integration. Now, but if we were to plug in numbers, we're plugging in pi over 2 and 0, and you would get this as your final answer. This again is very much the kind of problem that I might ask. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.